Let's get started. If you recall last time, we had introduced the weighted majority algorithm. This was to analyze the case of in which you don't have an infallible expert. So there is some expert, you don't know if any expert is right all the time, but you want to work as good as the sort of the best expert in hindsight. And the algorithm, weighted majority algorithm, let's just recall from last time, the weighted majority algorithm was we had this weighted majority algorithm, which for short, which the 0th step was initialize you. So for I going or for all the experts, initialize their weights to 1. You initialize the weights to 1. Then for all the time steps of the algorithm for 1 to t, you acted according to the majority of the weights. That's how we acted. Then step P, you observe the outcomes. And C, update weight. That is the WI t plus 1 is WI t by 2 if expert I erred and if otherwise unchanged. That was a weighted majority algorithm. And we wanted to compare how well does this algorithm do against the best algorithm, best expert in hindsight. So let's get some notation started. We want to analyze of WM algorithm. So what we want to ask is, what we want to understand is the number of errors of the WM algorithm in the entire time step from 1 to t. How many errors does it make? And we want to bound this in terms of the number of errors of any single expert, how single expert makes across time. That's the number of errors of algorithm rather. Let's define, even before that, let's define for each t going from 1 to t. Let's define MIT to be equal to the indicator is that expert I heard at step. That's just the indicator random variable. It's not a random variable, it's an indicator variable. And similarly define NIT to be the cumulative number of errors of expert I. That is summation of MIT T going from 1 to capital. This is for the experts. We'll do the same thing for the algorithm. MT will be indicator if the WM algorithm heard in step T, and similarly NT will be summation MT T going from 1 to T. And what we want to do is we want to compare NT versus NIT. In fact, minimum over I. This is what we want to compare. So how do we go about doing this? The heart of all of this is going to be, we're going to trying to understand all the, we are going to analyze 3 different types of algorithms today. And all of them, the analysis will be based on the potential function approach. We'll come up with a potential function. It's a very natural potential function in hindsight. It will be the sum of the weights. And we'll ask, how does this increase and decrease with time? So we're going to come up with a potential function with T for every time step T. This is just going to be the summation of the weights at that time step. And let's ask, how does this change over time? So what is it to begin with? Yeah, so initially each WI1 is 1, hence that's 0th observation, hence phi of 1 is n. No? Each time the WM algorithm errs, what do you know? WI decreases by a factor of 2. For all the things that have erred. So I'm asking the WM algorithm erred. The WM algorithm erred, that means majority of the weight actually got it wrong and all their weights were decreased. So in other words, in this case, then phi of t plus 1, I want to claim, is going to become phi of t is certainly going to be less than or equal to phi of t. Possibly half of it is not, but the 1/2 of it is going to get reduced by half. Do you agree with this? That is possibly 1/2 doesn't change, but there's another other half of it, each of which gets reduced by a factor of half. Therefore, each time this happens, so each time the algorithm errs, this potential function reduces by a factor of 3/4. So hence we're going to have Hence, at time t, we're going to have phi of t plus 1 is less than or equal to 3/4 times t into phi of 1, which is 3/4 times n. So it falls at least by this factor. On the other hand,
This is T is not time itself.
sorry. So this t should be n of t. You're right. Right? It falls by a factor of 3/4 each time a mistake happens. How many times you know that the mistake has happened? Possible, you know, n of t times. So for each of them, for the times mistake doesn't, the algorithm doesn't err, I'm not going to comment anything. Yeah, n of these are the sort of. M of t is the max that it earned in time of t, and n of t is the cumulative number of errors. So n is always going to, for us, stand the cumulative errors. If I index it with I, it's for expert I. If I don't index it, it is for the algorithm. And what we want to compare is this n of t versus ni of t. That's our goal. On the other hand, is a potential function. I want to also lower bound it for any expert I. If I errs in time t, we will have, what do we have? We have wi t plus 1 is equal to wi t by 2. Each time it errs, this is what happens. Hence, phi of t, I want to claim, is at least greater than wi of t. Certainly, it's a sum of all the wi of t. It's certainly this. Therefore, P of t plus 1 is greater than or equal to wi of 1 times half times ni of t. So P of t plus 1 is at least w1 of t plus 1, and that keeps on reducing by factor half each time that algorithm, that expert errs. Therefore, it's at least so much. And once again, this is therefore for any expert. So you put these together, you have for any expert I, we have the following. We have P of t plus 1 on one hand is bounded below by half times ni of t, is bounded above by n times 3/4 n of t. So this is the number of errors made by the algorithm. This is the number of errors made by the expert. So now let's just take logarithms and what are we going to take? Let's take everything to the base log 2.
What a better lower bound is summing over all the experts.
What?
Like, we just you could have got a better lower bound by summing over all the experts.
I don't, then yeah, okay. So you could have gotten, so this one will improve. Pi t plus 1 will become summation wi. So what you're suggesting is the following. Let me write that. What you're suggesting is the following thing. I can write pi of t plus 1 greater than summation wi, rather then just equal to wi t plus 1. and this is at least, sorry, summation I in n wit plus 1. And this is claiming, you want to claim this is wi w1, wi1 into half to the power ni of t I in n. That's all. You can do this, but the thing is, I want to just compare one expert again. I could do this also, except I don't know how to analyze. I don't know how. And the very next step which you're going to do here, I'm going to take a log of this. I don't know how to take the log of this summation and analyze it. Okay. And also, what you want to compare yourself against, if you look at it hindsight, you want to compare yourself against the expert for which NIT is very small. If all the experts are equal, this is off by a factor, then this bound is off by a factor 1 over n. If there are, so most experts sort of are performing equally likely. Suppose one expert stands out, then that expert is going to be the one that contributes fully to this sum. All the others will be dampened down heavily. Therefore, fact that we are lower bounding it to just the max of this is not going to really bother us that much. So the thing is, what I would think of it as, it's not an infallible expert, but there is one expert who hardly does any errors. Everybody else, so you want to pick that guy out. That person will have a large enough bound here.
Not losing anything.
Yeah. Yes. So now taking log 2, logarithms to the base 2. What do we have? We have, let's write it as log nt into log 4/3 minus is less than or equal to nit plus, this is log to the base 2 plus log n. That implies nt roughly 2.4 times. Okay. End of it, what I want to say is we proved the following. Here. Okay, I see it. After t steps, for every expert I, this is true for every expert I, we have nt is less than or equal to the number of errors committed by the algorithm is at most 2.4 times the number of errors committed by any expert T. We have that. And in particular, this holds even when I is equal to I star, which is the argmin of NIT. Even for the minimum, the expert which commits the minimum number of errors, it's more or less the same. So this is almost what we had last time. Suppose that there's an expert which commits 0 errors. This is basically we got the same thing except for this 2.4 factor. So you should think of this. This is a combination of both the infallible error. The infallible error says at least it takes you log n steps to focus on a particular good expert. And then in that case, there was zero errors. So you basically got just the log n. In log n steps, you eliminated it. You made an initial log n errors and then you managed to get it off. This is stating I'll do it, but then I will come to an error state in which I don't perform any more errors than the number of errors performed by the minimum, the experts which does the best in hindsight. You do not know who is this expert. This expert might change with time. That is, you run for capital T steps, it might be one particular expert. You run for another two T steps, it will be a different expert. But each time the algorithm is going to continue, you're claiming that whatever be that, you are going to perform at most 2.4 times the best expert who performs up to time step. Okay. Actually, it's quite simple. Actually, on the retrospect, you should look at this. It's quite a funny thing. The algorithm is extremely simple. It's hardly doing anything, but yet it is a guarantee, managing to guarantee such a powerful technique. What we will now do in the rest of the lecture, we'll ask several things. We'll ask if this 2.4 can be reduced. What we will show is, in fact, it can be reduced. The other one we'll want to ask is, can this log n be got rid of? This I will not do it in class. It will be one. Then your second problem set, one of the problems will be that. Notice this 2.4 was just a consequence of log 2 4 over third. So you can now ask, instead of doing it, reducing by factor half, you possibly reduce it by a different factor. So let's just try to do that. Let's just do weighted majority. So questions I want to ask. One is the multiplicative factor of 2.4 necessary? Is the additive term of order log n necessary? You should be able to sort of convince yourself the additive is sort of necessary. Even in the infallible expert, there's no way I can find out who that guy is. So we have an additive. Question is, can I come? If I can make this 2.4 to 1, it would be great. It basically says I take log n time to coalesce to the best expert, and then I perform exactly like the best expert. Though I have no clue who is the best expert. The algorithm is completely obvious. The algorithm hasn't yet found out who the best expert is. Possibly it does. It has the weight, expert with the largest weight at that time is supposedly the best expert. But this will keep changing with time. But irrespective of it, you manage to get. So we'll try to ask these two questions. The first improvement we'll do is we'll go from weighted majority to weighted majority with the parameter eta, where eta is some number between 0 and half. In particular, this only will alter. This only alters the update weights, in which case we are going to replace WIT plus 1 WIT with by WIT plus 1 1 minus eta. You're going to ask me why I'm doing eta and not 1 minus eta. It doesn't matter for now. We're going to think of eta as the small. Okay. The version of it will be this. This step will be replaced with well, let's quickly see what's the analysis of the the steps will be all very similar as before. 0 will be phi 1 of phi, not what you call, what did I call it? Phi of 1 is n as before, that's the initial step. Then each time t, the algorithm errs, what we have wi, rather we have phi of t plus 1 becomes smaller than phi of t. Possibly half of it is unchanged. The other half goes down by a factor 1 minus eta. So that is each time it goes down phi of t into 1 minus eta by 2. And the other case was each time t expert I errs wi t plus 1 becomes wi t into 1 minus eta. Once again, we'll be comparing phi of t plus 1. On one hand, this will be n times 1 minus eta by 2 into n of t. So it's originally started off with n and is reduced by factor 1 minus eta by 2 each time the algorithm erred n of t times. It's upper bounded. It's lower bounded by 1 minus eta to the power ni of t. Each expert. Let's do the same analysis taking logarithms on either side. So previously I took logarithms to the base 2 because one of them was a half. Now it's not, so it will be easier for me to take logarithms to the base e. It really doesn't matter. That just changes by a constant. But the reason I'm going to take log to the base e is we have Taylor series expansions for, we're going to eventually apply like log 1 minus x. We are going to approximate these by this one. We have them. It's easier to know these for when the base is e rather than this one to base e. So what do we have? We have nt into ln of 1 minus eta by 2 is less than or equal to ln n plus ni of t into ln of 1 minus 1 minus. All right. So hence that implies nt is less than or equal to nit. This is minus ln 1 minus eta by minus ln 1 minus eta by 2 plus ln n by minus ln 1 minus eta by 2. all the quantities I put here. The reason I'm putting minus ln is only then it's a positive value. Ln of a number less than 1 is negative, minus ln. So I want all the numbers I put here all to be positive values. So far, so good. So let's now use that. Let's use the Taylor series for ln 1 plus x. You know what the Taylor series for ln 1 plus x is? It's x minus x squared by 2 plus x cubed by 3 and so on. Then minus x power 4 by 4 and so on. It goes. What we so that is hence ln 1 minus x, which is what we care for in all these expressions, is actually minus of x plus x squared by 2 plus x cubed by 3. Okay. What we want is an upper bound of minus ln 1 minus eta to do this, and a lower bound of minus ln 1 minus eta by 2. That is because we want the inequality to go this direction. So we'll use the fact that minus ln 1 minus eta, which is just x plus x squared by 2 and so on, is upper bounded by eta plus eta, is just upper bounded by eta plus eta square if eta is between 0 and half. That is, I'm assuming that it's actually eta plus eta square by 2 plus eta cube by 3. I'm assuming that eta square by 2 is larger than the remaining thing. And the other one is just minus ln 1 minus eta by 2 is just greater than or equal to just eta by 2. If this is true, is just if eta is any number between, actually, if this is true, if eta by 2 belongs to minus 1 to 1. The first thing is just the expansion is actually eta plus eta square by 2 plus eta cube by 3, and it keeps on going on. Instead of eta square by 2, I'm putting an eta square, and that's upper bounding. Because eta is small enough, you can, the other terms will not contribute. Now let's go back, plugging. The following approximations. To start. We're going to get n of t is less than or equal to ni of t. The numerator is eta plus eta square. The denominator is eta by 2. Yeah, now I remember, now I realize why I used epsilon in my notes. Because I think my eta and n are too similar. Plus ln n eta by 2. So this is 2 into 1 plus eta nit plus 2 ln n by eta. We must have a similar theorem to this.
So you can take eta to part between this one and
Yeah, you take, there's a trade-off here. That is, you want as close, if this one will get you as close to 2 as possible. You make eta large enough, this goes very large. So there's a trade-off between the two. 1 plus eta ni of t plus 2 ln n. But it's still not what we wanted. What I wanted is, I would have wanted to eliminate the 2. What we did was made the 2.4 to be 2.001 or some such thing. We didn't get it to be 2. But of course, it came at the cost of increasing the constant before the ln n. People try this out and then they realize this any such algorithm actually cannot do better than 2. This factor 2, not just the weighted majority algorithm, no algorithm can do 2, but no deterministic algorithm. So in fact, this will also be a problem in this one question. I want to ask, can we go below 2? And thing is, the remark is, no deterministic algorithm can obtain a multiplicative factor less than 2. And the way, so in fact, in the problems that you will come up with this counter example, I give you a deterministic, you give me a deterministic algorithm. And for that deterministic algorithm, you can give a sequence of ways in which that, in fact, you can just give a just two experts. Forget about number of experts, just 2. You can give a way in which you err such that every deterministic algorithm will commit at least twice the number of errors as the best expert. So what we will now do is actually ask if randomness can help. And that's finally, so the question is, can randomness help? And the answer is going to be yes. Instead of choosing weighted majority, algorithm makes a decision, makes a random decision distributed according to the weights. And basically, the reason the half is coming is, suppose the weights were more or less balanced. Because one weight was, I'm normalizing the weights. One was half plus delta, other was half minus delta. The deterministic algorithm was going to put reference to half plus delta. But then the other guy is also, you can now ensure that the other guy is the correct. So you have a factor of 2 difference. So now you want to ensure that if it's half plus delta, half minus delta, you sort of put equal weight on it. So you toss a coin which is half plus delta heads and half minus delta tails, and pick the coin according to that. So then you are equally likely to go to the other. You're going to put even weight on half minus delta, and that half is actually basically the 2 that is coming up in the. You can't go below the 2. This is how you build up the counter example. Proof that is because if you're doing it deterministically, when the weights are more or less balanced, you're just slightly preferring the guy over half. Then there's no reason to do that. It possibly is just noise over there. So instead of it, you choose it according to random point, which is biased based on these things. So that's what we'll do. But actually, then, if you're just analyzing this algorithm, what we'll observe is this one works not just for, so far we assume that there are just Boolean outputs. Now we'll actually, this randomized thing works for a far more general setting. So we'll assume that each algorithm, each expert is predicting some advice, and we are going to follow the expert's advice or not. The advice could be one of several actions. It can be a continuum of actions or any such thing. So far, we assumed it's one of two actions. So we'll assume it's a continuum of actions. It could be anything. All that we are going to say is there is a loss function associated with each expert. Previously, the loss function was either 0 or 1, either it erred or did not err. We will now assume that there's a loss function which is between -1 and 1. So the law, if it is lossy, it is -1. If it is actually going to be correct, it is 1. So if we're putting a loss bill, we're going to put a real number between -1 and 1. Only thing we're going to assume it's a bounded loss function. That is, if you compare the different losses of the across the beam, they are all bounded by a fixed number, and that number we call 1. It could be that this algorithm doesn't analyze a case in which the loss of one expert is way unbounded compared to the other. We don't know how to analyze it, but right now we'll analyze this using the weight. This will be our final multiplicative weight update method.
So the weighted majority algorithm does it not work in a continuum where there is a loss function defined?
So it's unclear how you will define. So in a continuum, what does it mean to do weighted majority? So weighted majority, very fact that majority, I said majority meant that there were two choices, and I chose the majority choice, whether this way.
Now we can take a weighted average.
But weighted average according. So suppose there are 10 choices, you take the weights, and there are two choices, both of which let's say no choice is going to get. It might be that no choice gets a majority. Okay. Say there are three choices, and they all get like slightly. So assume they're not equal, but you sort of get one third, slightly more than one third. How do you? If two choices get the same, how do you choose it? The randomness, let's say pick both of them equally likely.
The same issue will come with MWA also.
You'll see the analysis; it will not come. So if you do it randomly, so what we'll analyze the expected number of errors. We will not analyze the worst case number of errors in any run. We're going to analyze the expected number of errors, and that will get rid of this. In fact, I don't care what the predicate is. I don't care whether the advice is yes or no. I'm just going to say they're going to give some advice. One of 10 choices, this choice. All I'm claiming is there is instead there is a loss function. MIT between -1 and 1 for each expert. Right? Previously, this MIT was a number which was standing either 0 or 1. Now I'm going to say it's some number between -1 and 1. It's a loss. So when you observe, you see the expected losses of all of them. In particular, general, I'll talk MT to be this vector. MT to be this vector M1T, M2T. We'll talk about this vector. And we'll also have, of course, we'll maintain weights as before. We'll have the weights, the weight vector WT, which will be W1T, W2T, WNT. But now we'll also have a probability vector. These are the weights. I will want to know the probability vector is going to be, this is the weight vector. This is the loss vector. Weight vector. Then we have the probability vector. P of t, this is the distribution. It's P1 of t, P2 of t, N of t, where Pi of t is exactly weight I of t. It's normalized by the sum of the weights, which we recall we called it phi of t, and phi of t is
Prediction will also continue.
huh? So I don't care what the prediction is. I'm going to say each expert gives you an advice, and I'm going to have weights for all the advice. I will pick a coin according to the distribution of weights. If I get the coin, so it's an n-sided coin based on these weights. If the coin says particular, say the coin comes up high, I'll just go and do whatever the ith expert says. Whatever the advice ith expert says, I do it. And then I get so let's just write it down. Let's just write it down. So once again, this will have a parameter eta, which is that means instead of calling it eta, let's call it epsilon. Epsilon between 0 and half. The first step is as always initialize for all experts. We're initializing the expert weight to 1. Then for each time step, for t going from 1 to t. Now you choose an expert I. Choose an expert, choose a decision. Choose an expert I. According to the probability distribution Pt equals P1t, P2t, Pnt. Whereas before Pit is Wit divided by phi of t, and phi of t is the normalization. So you just act according to whatever that expert does. It could be a binary answer, whatever answer. B, then observe the outcomes. That is basically at this point of time, you have observed the vector mt, which is m1t, m2t. You observe. So you get to observe what is the loss that each of the experts incur. Notice that sometimes this might also be too much to ask for. You might only be able to observe the loss of the expert whom you, for example, several people make predictions. You follow that, you only know your loss, you won't know what is that. But in these algorithms, I'm assuming that you have got the losses of all of them. See? Update weights. That is for each I in n. We're going to replace Wi t plus 1 to be WIT into 1 minus epsilon times MIT. This is exactly what we had done. Previously, MIT was a 0, 1 vector. If it was 0, it remained as it was. If it was 1, it shrunk by a factor 1 minus epsilon. That's exactly what we have here. That's going to be our entire algorithm. Is the algorithm clear? Want to analyze the So what we want to analyze, we want to analyze the expected loss of the algorithm. So let's notice it's a randomized algorithm. So expected loss of WMUM algorithm at time t. What is this? This is going to be, this is exactly this quantity. You denote it by L of t. This is exactly summation I and n because you're choosing a random behavior. So PIT times MIT. Because that's the probability which we are taking the ith expert's action, and that's the loss of the ith expert. Therefore, that's your expected loss. Or this is just in short form, this is just the inner product of MT, the vector MT with the vector PT. And what we care about is cumulative expected loss. That is L of t going from 1 to t. This is just summation t going from 1 to t. MT. Okay. As before, what we want to compare, if we want to compare L of t versus summation t going from 1 to t, MIT, in particular the minimum of this overall. That's the loss of the expert, any expert I, and so it's the best expert doing it. We want to compare L of t against this. Is that clear? And we will do more or less the exact same analysis. We will use the same potential function. We'll analyze it as before and find out how things change. So it will be phi of phi1 is going to be n initially. Let's ask, how does PT plus 1 behave with respect to PT? So what is PT plus 1? This is by definition just sum of WIT plus 1, I in n. But this Here's the updated weights. It's WIT into 1 minus epsilon MIT. I'm going to drop this I in N and just put I. Should be clear. Okay. This is just, so I'm going to break the summation. Just the summation WIT into 1 is phi t minus epsilon MI minus epsilon times summation MIT into WIT. But what is this quantity? I want to say this is exactly. I want to say this is exactly P of t minus epsilon times phi of t summation MIT PIT. Because PIT is exactly WIT by phi of t. The reason I want to do it, and this is where the multiplicative, so the way this is going as 1 minus epsilon times MT and typically we use the step to say it decreases by each time. So it's decreasing by this factor each time. It is shrinking by this factor each time. It'd be nice to work with this factor. So what I'm going to now say, this is actually less than or equal to P of t into exponential in minus epsilon MTPT. Since 1 minus x is always less than or equal to e power minus x. Okay. So what do we have at the end of it? We'll have that phi of t plus 1 is less than or equal to n times x spin minus. So each time it shrinks by this factor. So over time steps, each time it shrinks by this multiplicative factor. So it's epsilon times summation t mt pt. Is that clear? It's a product, but it's in the exponent, therefore it becomes a sum over. So phi t plus 1 is upper bounded by this quantity. But we also know the same thing. We have the same thing for any expert I. We know that Wi t plus 1 is equal to WIT into 1 minus epsilon MIT. Therefore, hence P of t plus 1 is greater than or equal to Wi of t plus 1, which is exactly equal to 1 Wi1 into product of 1 minus epsilon MIT. This is the product is going over the t's. Okay. Once again, I'm going to do the proof in a slightly more general fashion. Previously, MIT for us was only a number between 0 and 1. In fact, it was only 0 or 1. I'm going to relax it and let it be 0 or 1. But now I'm going to allow not just, I'm going to write the proof more general. Sometimes I'm also going to say there is losses, there are gains. I'm going to say the gains are more than this one. So I'm going to allow MIT to the way I assumed it. I'm going to assume the MIT vectors were in -1. Not just 0, 1. So what does that mean? This actually, sometimes actually the weights increase. So sometimes it becomes 1 plus epsilon. Suppose MITs are 1, 0 and minus 1. Sometimes it's unchanged. Sometimes it increases by a factor 1 plus epsilon. Sometimes it falls by a factor 1 minus epsilon. We'll take all of that into account. Okay. So what I want to say, and I want to do this lower bound. So let's first split this as by t's in which MITs are greater than 0, 1 minus epsilon MIT, drop greater than or equal to 0. So t's in which MITs are less than 0, I want to put a lower bound. I want to say this quantity is larger than 1 minus epsilon. Right. That right. Let me drop this. I'm just going to put the greater than equal to 0. This is the less than equal to 0. Clear what I mean by those two. We can technically drop the equal to 0. Let's just keep greater than 0. What do I mean? Why is this true? Since I think I'm using the following. 1 minus epsilon x is always greater than 1 minus epsilon to the power x if x is in 0, 1. Is that true? True.
This happens if it's positive, then it will happen.
Huh?
If X is positive, then it will happen.
Why does this happen actually? It doesn't. So, and I'm basically trying to say these both. One, similarly, I'm stating 1 minus epsilon x is greater than or equal to 1 plus epsilon to the power minus x if x is what is right? The expansion right.
Epsilon is positive.
Huh? Epsilon is a number between 0 and half. What I have, but this is obvious. Why are these true?
The cornerstone, I think we can see from the Taylor expansion of 1 minus epsilon. We can look at the Taylor expansion.
So which one will you see first? You expand this by Taylor, you get 1 minus epsilon x plus epsilon square x square. But why is this? What a feel. Isn't it going in the wrong direction? Yeah, these are the directions I want. Do you quickly see why this is true? I thought it was obvious. No, I don't see it obvious at all. Around. I don't know, I'll have to check this out. I don't see it right at the top of my head, but this is the inequalities there. This is huge.
We could take the log.
We need to take logarithm. You have to do Taylor of this or not Taylor using with epsilon being the variable. X should be the variable. So you have to take 1 minus epsilon x and do a Taylor of it around the point with x as the variable around the point 0. Therefore, what will it be? It will be think of it as e power x times ln 1 minus epsilon. Therefore, the first term it will be 1 plus x ln x. There will be a whole bunch of terms. Therefore, I still don't see why this is the case. Put it in the survey of not just mine. This morning I thought I checked it. Okay, let's take this one and I'll add a note for this in the one later on if I see. So this just becomes equal to pi grade. It just becomes 1 minus epsilon into summation MIT over the greater than zeros and 1 plus epsilon summation minus MIT for the less than zeros. Once again, comparing hence. We have 1 minus epsilon to the summation MIT greater than 0 into 1 plus epsilon minus MIT. This is less than 0. We know that this quantity is less than or equal to n times what was the bound we had here? X of minus epsilon notice that this quantity is exactly what this is the number which we carry. This is n times x post minus epsilon LT. That summation MTPT was LT. Now we just need, let's do the take logs on all sides. So what are we going to have? We're going to have LT as an epsilon ln t is less than or equal to ln n plus summation MIT greater than 0. This one into ln of 1 by 1 minus epsilon minus summation MIT this is less than 0 of ln of 1 plus epsilon. Is that right? Yeah, that's fine. So this is once again we're going to now upper bound it by ln n plus summation MIT. This is just those MITs for which are the MITs are we have fixed a particular expert and these are the MITs for which they are all positive. We want to, what do we want to do? We want to upper bound ln of 1 by 1 minus epsilon. What was an upper bound? We already saw an upper bound for ln of we already saw an upper bound for where was that? So minus ln, where is it? Minus ln 1 minus eta is we bounded by eta plus eta square. So let's just use that upper bound. Into epsilon plus epsilon square. Then there is a minus summation MIT less than 0. Let me make it a plus and make it absolute value of MIT. The MITs are all negative. Therefore, taking an absolute value so that all the quantities look like positive. I want to now what do I want to do? I need to bound ln 1 plus epsilon from above, and this one epsilon bound from above is epsilon minus epsilon square. So this is this is an upper bound. Sorry. An upper bound. So plus epsilon times summation MIT. 1 second. Okay, let's go here again. Sorry. Mess it up again. On 1 plus x is epsilon minus epsilon. That is right. That is right. LT is less than or equal to ln n by epsilon. Then epsilon will go away from the plane. This is summation MIT plus epsilon times summation MIT. That's what I have. Check. Minus sign somewhere. 1 second. Right. Epsilon plus epsilon square. That is right.
If you don't take the mod, then
No. So this minus always, or this is actually a plus over here. That I flip the sign somewhere.
plus
This is a plus. Yeah. Then things work out. It's a plus, therefore there's a minus mod MIT, and then everything works out. So what am I claiming here? So the theorem is the following. Notice this is at the end of t steps.
I think you still use epsilon plus epsilon, the other bound, right?
Huh?
Epsilon plus epsilon square.
So I use no. So I'm using 2 bounds here. 1 bound. So let's figure out what are the bounds I'm using here. Let me write down the bounds. One, we are using ln of 1 by 1 minus epsilon is less than or equal to epsilon plus epsilon square. That's the first one which I used. And the other one I'm going to use ln of 1 minus epsilon I want to say this is greater than or equal to epsilon minus epsilon square. Because that comes with a negative sign, I need a lower bound on it. And it's greater than epsilon minus epsilon square.
But for this to follow, what you want to do is, so that plus, you break into two minus, one you use the mod.
So I don't have to, so you can forget about the mod over here for now. Just keep it with the minus sign itself. Let's just keep it with MIT. So, but ln 1 plus epsilon, what I need over there is a lower bound because the MITs that come before it are all negative. I need a lower bound on it, that is epsilon minus epsilon square.
But then how is the third term?
The third term, what happened? Which one?
The third term in the last equation.
In the last equation, so how do I get this? The epsilon goes. Once again, you're right.
By 1 plus epsilon, that is less than epsilon plus.
No, this is ln 1 plus epsilon, firstly, sorry. And this is, I believe this is minus epsilon. This is what it should be. It cannot be this. It cannot be this. 1 second. I'm messing it up again. That is right. What I had there is right. Once again, let's just check how I messed up when I messed up over here. This so far, am I right here? So far, I'm right. So this is 1 minus epsilon, this one 1 plus epsilon, that is right. Then when I take logarithms, what happens? When I take logarithms, I should have done it all in one set. So ln n is ln n. When I take logarithm, this minus epsilon ln t becomes minus epsilon ln t and it becomes epsilon ln t this side. That one goes as summation mi ln 1 minus epsilon. When it comes the other side, it becomes ln by 1, ln minus ln 1 minus epsilon, which is ln 1 by minus epsilon. The other one, there's a minus MIT ln 1 plus epsilon, and yes, this has to be a negative sign over here. That's fine. There's a negative sign over there. So now I need an upper bound on ln 1 by 1 minus epsilon. Therefore, I use that. Epsilon plus epsilon squared. I also need
This minus, and we brought it to the other side.
which minus? No. So you're claiming that minus becomes a plus here.
Then
Yeah, this minus is a plus. That right? That right? Yeah, fair enough.
so you can take a mod there.
No. So now it is fine. No, it's MIT epsilon plus epsilon square plus MIT epsilon minus epsilon square because I need a lower bound for this because the MITs are all negative. So you have, that's why I have this quantity. And now I'm fine.
ln 1 plus epsilon is also upper bounded by epsilon plus epsilon square, right?
Huh?
ln 1 plus epsilon is also upper bounded by epsilon plus epsilon square, right? Understand?
No, but here I want a lower bound because if the thing multiplying it is a negative quantity, so I want a lower bound on it, and the lower bound is epsilon minus epsilon. For this, I want an upper bound. For the ln 1 by 1 minus epsilon, I want an upper bound, which is fine. For these guys, I want a lower bound, which is what this is. So let's talk about this. That's what I had. So this is what is this? This is, so I get a ln n. The epsilon's nicely, so I get a plus epsilon times summation MIT. This is for all MIT because both the positives and negatives. The other one, I get it with an epsilon square MIT, but I get it with an absolute value. This is summed over I. This is, sorry, not summed over. Hence, LT is less than or equal to epsilon MIT plus epsilon times plus ln n to the end of t steps, the expected cumulative cost. Sorry, I made a ton of errors over here. So it is ln n by epsilon. That's the rate of the algorithm. Plus, that's the most important thing. It's MIT. That's the loss of the ith expert. And it came with the constant 1 in front of it. That's our most important thing. Plus, there's an epsilon times for any expert. So in particular, if it was our previous case in which MIs were just 0 or 1, this is just 1 plus epsilon times MIT, the loss of the ith expert. So it's almost you get all the way up to the loss of the ith expert. This I unnecessarily confused putting MITs to be positive and negative. That's because for a later application, I need it for lecture 3 or lecture 4 from now. So I'm allowing MITs to be also be negative 1 here. And if you do that, this is what it comes. So the nice thing about it is once you allow for randomness, the constant, previously the constant out here was like a 2 into 1 plus something. It's become a 1 plus something over here. And also this error notice, previously it was ln n over 2 by epsilon. It's become 1 over epsilon. You shaved off the factor 2 completely. Randomness helped you to do that. You got this. This will be our final one. We will work with this and we will see several. So far, sorry, I made a lot of calculation errors on this. I'll check over it again. If I have any errors, I'll fix it in notes before I post it online. But the heart of it is this algorithm. And it's a very clean algorithm and a very simple analysis. We will show how powerful is this by seeing a whole variety of completely unrelated applications. And we'll see where this can be useful and we'll see how it is. That's what we'll do in the next. So in the next 3 lectures, we're going to see various instances where you're going to use this algorithm. You will see one slight modification of the algorithm and then see various instances where you'll be using this algorithm. That's going to be the plan for the next 3 lectures. For the end of this module of weighted multiplicative update method. Okay, let's stop with this.